Hey everyone, thanks for joining me today. Dr. Boltin here. Um, and today I want to talk to you guys a little bit about the area of data science. And so this course is data mining and predictive analytics. And I've really designed this course to kind of be a bridge between the area of what we consider traditionally as computer science and data science. And more specifically, the area of biomedical informatics. And so in this lecture, I'm going to cover some of the areas that pertain to data science in general and how it relates to biomedical informatics, and talk to you guys about a couple of the tools out there that are important for data scientists to use. All right, so let's jump into it and we'll get started here. So before we get started with this, really to understand biomedical informatics and health informatics, we want to take a look at a couple of the subfields within this area. And so there's a lot of different subfields in this area. I've put this table together to kind of help you guys take a look at each of the ones and what they're described as, and some of the helpful skills if these areas interest you. Some of the skills that might be helpful to make you successful in each of these areas. So bioinformatics oftentimes is related to DNA, protein sequences, things like that. Biostatistics is really the area of applying different mathematical principles to different health and bio-related subset data sets. Computational, and that's closely related to computational biology as well. Clinical informatics usually has to deal with more of the data that we're capturing within the healthcare system. So that and public health informatics are oftentimes tied in, related to health records, that kind of information. And so oftentimes the skills that are important for that, we'll talk a little bit about this today with big data. But understanding how to apply decision support systems using machine learning and AI. Public health, oftentimes dealing with wearables, wearable devices, mobile health, electronic medical records, things like that. And then the little sub area of imaging informatics is really becoming more and more popular these days, but oftentimes dealing with predictive accuracies of looking at different imaging formats, especially as it pertains to like X-rays, MRIs, PET scans, things like that, to be able to glean and look at information being captured from these systems. So here at the University of South Carolina, there are a lot of people working within the informatics area. And so I didn't capture all these in the slide, but these are just some of the ones that are related to this particular lecture. And so in biomedical engineering, we have instrumentation. At least when I taught it, there was a lot more of informatics related topics within that course. And the modeling and simulation course as well. I hit on some of these ideas within that course's. Also, I teach that course. Within the computer science area, we have algorithm design. Those are important courses to take if you want to take any advanced courses in computer science. So oftentimes these are prerequisites for many courses that you would take later on down the road. Some of the faculty work in this area, obviously myself, but also Dr. Hugh, who also looks at different bioinformatics issues, material informatics, and health-related informatics. Dr. O'Reilly has done a lot of research in AI and machine learning as it relates to neuroscience. And so he does a lot of work with like autism and things like that. Dr. Valafar is a more of a bioinformatics guy, and so he does a lot of computational biology as well, and does a lot of computational medicine. And so these are all faculty. Dr. Sheth was a founding member of the AI Institute. He does a lot of NLP, chatbot related stuff. And so these are some of the faculty that are working and doing research in these particular areas. There are more faculty as well, so if you're interested in that, just reach out to me. All right, so really, I put this in a little infographic together to kind of get you excited and get you started about this. This comes from a website called Damo.com, and this is a website that puts this together every year. So if you want to see the most up-to-date stuff, you can go and actually look at it. They should have stuff up there by now, but for 2023, maybe even 2024 now. But they really analyze data annually and what it's used at today. And so really 90% of the data that we see today was created within the last 3 or 4 years, and this is due to a lot of different elements, a lot of IoT now that is involved, and the pandemic really brought forward a lot of these companies. So just some of the statistics from this graphic that I think are pretty neat. Things like 16 million text messages are sent every minute. Snapchat users are snapping 2.43 million snaps every minute. And within the Google area, there are 5.9 million different searches every minute on Google. And DoorDash became very popular during the pandemic with, at its height, $76,000 worth of orders every minute as well. So you can see that we generate a lot of data every minute, and therefore we need to come up with different, and obviously we can't analyze a lot of this in the traditional sense of the way that we would look at data, and so we have to come up with sophisticated ways to be able to analyze that, and that's where the area of computer science and data science come into play. So what is data science? So data science is really a multidisciplinary field that utilizes scientific methods, processes, algorithms, and systems to extract knowledge. So this is important not only for different data sets that are either structured or unstructured. And so what I've put together here is just a Google Trends graphic that I have. If you guys are familiar with that, Google Trends is a website that Google has that analyzes the popularity of top searches within the Google search. And so what we see here is we can compare different terms that you can search within Google and see what their popularity are. And so you can see over the last 10 years or so, the terms like data science, data scientist, and statistician have all grown exponentially. And so when we look at the area of data science, like I said, it's a multidisciplinary research area, but what are the actual components that are going to be important for someone who is interested in looking or becoming a data scientist? And so oftentimes when I first started looking at these terms, the popularity was really data scientist as a glamorized statistician. And in a lot of sense, that's somewhat true. Data scientists actually started off as computer programmers and machine learning experts who were working on these kind of big problem data sets. And they were analyzing different data sets that traditional statisticians really didn't want to mess around with. And so these were things like emails, image files, HTML files. And so a lot of statisticians weren't interested in these type of mathematical problems. And so a kind of like subgenre of data science was developed. So some of the things that are being important for data scientists to gain skills and is one, you're going to have some kind of root foundation in statistics. Sorry if that's not your strong suit or you're not interested in it, but you're going to need to understand what statistics is and how to use statistics to really glean information that you're trying to get. And so you'll have a root foundation in mathematical statistics. And it really just deals with the different mathematical methods for being able to solve different problems. Data engineering, so there's skill sets for being able to manipulate and really modify data to really gain knowledge from that. And so you're going to be really good at being able to look at data, gather data from different sources, and manipulate data to help. And we'll talk about all this as what this course is really to try to understand how to modify and engineer data. Advanced computing is part of it, so understanding how to look at different resources for being able to do different GPU computing and different ways that we can actually analyze big data in different ways. Visualization is important for being able to communicate your findings and communicate knowledge to individuals who really don't have a background in this area. And so understanding how to present that information to individuals is important also. And so visualization as it pertains to being able to communicate your ideas and knowledge to other individuals. All right, and then really the thing that you guys are working on within the university setting is gaining some kind of domain expertise. And so this may be in all kinds of different areas, and this is really personalized to yourself. All right, are you interested in biomedical engineering? Are you interested in finance? Are you interested in e-commerce? All right, healthcare, all of these things are decisions that you will have to make on a personal level as to what area do you want to be able to apply data science and what domain do you want to apply it. So some of the examples of different data science applications in general, all right, these are things that you're using on a daily basis. So you do tons of internet researches, not only with Google, but also like Yahoo, Bing, Ask, AOL, all these different search engines are making use of data science algorithms to really deliver the best results for your searches. All right. Recommendation systems. So you guys use things like Netflix, right? Prime, all of these. Also, Amazon, Twitter, LinkedIn, all of these are using recommendation systems, a priori analysis to be able to look at what you guys have previously searched and give you a better result based on your previous searches and other people's searches. And so recommendation systems. Image recognition, things like Facebook is really led the way in this area. So like when you take pictures now, they can recognize the face within that photo, pop up a recommendation of, hey, do you want to tag this person in your photo? Do you want to tag this location? All of these different recognitions are being used now within images as well. So these are some of the general things. Another example I'd like to give, this is a little older. I think this was 2015. I thought this was a neat article. I read this article in 2015 that came out about Google Translate. So back then, Google Translate really wasn't all that popular, and so as it is today, I'm sure if you guys have traveled to any other countries, you probably use this quite a bit. But back then, it really wasn't that important, and so Google put out this white paper that really didn't get any kind of attention. But I read it, and I was blown away that Google was able to do this. And so Google Translate actually ended up inventing its own language to help translate languages more efficiently, and it was called zero-shot translation. And the idea was that in the English language, if you were trying to convert, say, English to Korean, right? Oftentimes there are words that are in English that aren't directly translated to the Korean language. And so what Google Translate figured out was that since it can't translate directly from English to Korean, because there wasn't a word for that particular language, that it did figure out that it could translate, say, Japanese. There were words for Japanese to Korean for that particular word. All right. And so then it decided that it was easier for it to translate English to Japanese first, all right, and then translate Japanese to Korean. All right. And so it did this on its own. Which I thought was fascinating, which was really, really cool. but it didn't get the recognition that it really deserved until years later. And now, I mean, we have ChatGPT and all these other large language models, but this was really at the beginning of all this kind of taking place, and was really a fascinating article that that it was able to do this on its own. Applications that we see, this is more specific to biomedical engineering, and really more specific to some of the things that we do within my lab. And so things like biomonitoring, looking at heart rate, EEG systems, so brainwave activity, heart rate activity, eye movement, muscle movement, all of these things. These are different biomonitoring techniques that take advantage of the electrophysiology of the human. Also building decision support systems to help our healthcare workers make better informed decisions about recommendations that they're giving to their patients. All right, and so this is important for a lot of different areas of healthcare. Some of the other more general applications that we're now seeing, machine learning, data science, now be integrated into a lot of things within the area of, say, personalized medicine. So now scientists are utilizing our own genetic content, our own DNA, and other molecular analysis to be able to provide personalized medicine and treatments for many, many different diseases. Wearable devices. So we talked about biomonitoring, but there are now a whole slew of different medical or personalized wearable devices. Apple Watches, many of you guys are probably using these types of things that have things like heart rate monitors to be able to track your training performances and things like that. Calorie counters, speed, distance monitors can all be done. Sleep monitors. There's a whole bunch of other things out there, such as like wearable belts for being able to monitor respiration rates. Smart clothes that have like built-in accelerometers and gyroscopes for being able to analyze all kinds of performance metrics. More and more popular nowadays are the ideas of having mobility and cloud access, and so AWS, Azure services, all of these are now becoming integrated into a whole area called mHealth, all right, mobile health technology, and so tons of consumers and tons of physicians are now interested in this area, and how can you integrate mHealth and cloud access to these different areas, and so very, very becoming very important. So you've heard me use this term quite a bit. I want to define a couple of these terms a little bit more for you guys. So what is machine learning? A data analysis method that automates our analytical model building, and I'm going to talk a little bit about what the differences are in there. This allows us to make data-driven predictions and discover different patterns, all right? And is useful when we have very complex problems and lots of data, what we call big data. Some other terms that you might notice or might hear about or read about in some of the literature that are associated with machine learning are things like data mining, predictive analytics, obviously this is the title of this course, AI, artificial intelligence, or pattern recognition. There's just some of these terms that you might see out there. So what does this term big data really mean? So it really refers to data sets that are really too large, too complex for traditional data processing. All right. And oftentimes deals with three different areas that I like to define as being determining whether or not you have big data or not. And that's volume, velocity, and variety. So data volume really has to do with the quantity of the data that's being generated or stored, right? And so this is the size of the data. So imagine that if I have like just a spreadsheet, a nice little Excel spreadsheet with a few, even 1,000 rows and I don't know, hundreds of columns, that still might be on the order of say kilobytes or megabytes as far as like size. All right. And so how much information can I glean from just that one single file? So imagine, otherwise if I have a whole database system that is full of all kinds of different tables. They have relationships to one another. All right, databases can be on the order all this financial data, or another popular one is airport traffic control data coming in. All right, all of this data might be on the order of terabytes or petabytes, much larger amounts of data. So imagine that. Also, the variety of data that we might have. So I talked about an Excel spreadsheet. That's just a table. So that's at the small center of this particular graphic, right? But imagine if I'm using a database with even more and more tables involved, more and more relationships involved. All right, that moves out further and further to being larger and more amount of data. And then also, if I have different types of data, so not just an Excel spreadsheet with numbers and cells, but say I have photos or PDF files or web addresses or websites that need to be analyzed or audio files that have to be read. All of a sudden, this whole variety of data becomes much more complex. And then velocity really has to deal with the way, or the amount of times that I'm collecting the data. So the speed at which that data is actually being generated. And so again, to my table, my Excel table, that just might be a one-time batch collection, one snippet in time of a particular data set. But imagine that I'm collecting things near real time or in real time, which is in most cases for most, near real time in most cases for biomonitoring devices, right? So imagine I'm collecting heart rate or blood pressure or all of these things, every second. So in some kind of frequency. So every second or every millisecond. All right. That data velocity is much more increased at that time. So if I have large amounts of data that is being collected, and it's a huge host of different types of data, and it's being collected in near real time, I have a large collection of complex data, right? And so now you're dealing with big data. And so that's really a more definitive definition of what big data is. And really the area of healthcare, biomedical informatics, medicine is really ripe for this type of data-driven revolution. And so data science can really deliver breakthroughs in all kinds of areas, all right? Such as genomics, all right? So genomics is really our understanding the function of the genome, right? And how it relates to human disease. And so I like this graphic that was published in 2015 by PLOS, all right? And what we see here is that in the area of genomics, we all know that the Human Genome Project was completed, I think in like 2003. And this has really paved the way for really personalized medicine and the growth in this genomic research. And so this article that was published in 2015 showed that the amount of data that we create in genomics alone every year eclipses more than all the tweets that were put out that year, all the information that we collected in astronomy, and all the information that we had on YouTube. All of those combined, we're building more and more information from the area of genomics. So in this slide, I just want to try to look at how machine learning. So this is we just talked about some of the applications of machine learning and AI, but what is really going on behind the curtain a little bit. And so oftentimes machine learning requires us to kind of change the way we think as computer scientists, right? And so back in the day when we were doing traditional programming, when we were creating traditional programs for computer science, this is kind of how the flow worked for doing that. Say I had some data, all right, and I have a program, and then I have a computer, and that computer is going to create some type of output. Best example I can give you of this is like your calculator, right? So if you have a calculator, Your data is going to be the values that you enter into the calculator. So say I enter the value of 2 and 3. The program itself is actually going to be addition, subtraction, division, whatever, mathematical method you're going to apply to these numbers is your program. So here we add just the values of 2 and 3 together. That calculator is actually going to do the computational work on that, and it knows it takes the values 2 and 3, adds them together, and gives you an output of 5. All right, this is the way traditional computing methods work for a long time. Well, come along, the area of machine learning. All right, we kind of have to train our brain to think a little bit differently. So in this sense, with machine learning, we have a set of data. We're going to actually also give it its output that we want, and then that computer is going to generate the program for us. So if we go back to our calculator example, if I enter in the values of 2 and 3 again, I'm going to tell the computer that I want the output to be 5. And then the computer is going to generate the program that is necessary for us to be able to get this output value. So in machine learning, the two biggest things to understand is that, one, we're trying to generate this algorithm, this program that we want to generate this specific output. All right, that's the biggest thing to understand when we're looking at how machine algorithms work and how to design them from a computer science perspective. So the way that we do this is there's two areas of machine learning that are important for you guys to understand. You have supervised learning and you have unsupervised learning. All right. In supervised learning, that is exactly what we just explained. You have a known response, right? You have that known output that you need to understand. So if I have some data and I know what the responses are, I can then apply some new data to that model and get a predictive response. So in this case, if I'm looking at this set of data that is just generalizable, I have a Star Wars character, all right, a DC character, and a Harry Potter character. All right, or any of these, and I can create a model that tries to characterize whether I have a DC, a Harry Potter, or a Star Wars character, right? And so then I input some data that it's never seen before, which happens to be a Marvel character or DC character here. And then it tries to place it into the algorithm that is associated, or place it into the category that is associated with its known response. So in this case, as a value of yes, right? And so the big thing to understand, and we'll look at specific algorithms related to supervised learning, is that we're trying to predict an outcome, and for us to be able to do that, we need to know what that outcome is going to be. And you'll see a lot of this will be a common theme later on the semester when we really get into these machine learning algorithms. Unsupervised learning, on the other hand, is really looking for patterns that are associated with our data. So if I have an uncategorized data set, all right, I just have a whole host of different characters here in this particular example. All right, my algorithm I don't need to know what the response is going to be for our particular outcomes, all right, because the algorithm is just going to cluster this large amount of uncategorized data set into categories based upon related characteristics, all right? And so what ends up happening is that we have different outcomes, but these are all related to each other based upon certain characteristics. And so we're clustering the data based on certain characteristics, all right? So big two areas to understand with machine learning. All right, more specifically, these are some of the actual algorithms that we'll be taking a look at this semester that are related to supervised and unsupervised learning. Again, supervised learning has to deal with being able to predict. We need to know what our inputs and outputs are going to be. We can do classification and we can do regression with supervised learning models. And these are some of the algorithms that are important for each of those. All right. We'll take a look at naive Bayes, nearest neighbor, neural networks, decision trees later this semester. All right. Supervised learning, again, has to deal with the clustering. This is more based upon those internal characteristics to be able to characterize data based on their features. All right. So k-means is important. Fuzzy c-means, all right, neural networks. You can see that some of these overlap. All right, neural networks can do supervised and unsupervised learning. And then hierarchical clustering as well are some of the ones that we'll take a look at. All right, almost to the end, but let's talk a little bit about some of the computational tools that are important for computer scientists that are working in biomedical informatics and big data. All right. Obviously, the big thing that separates data scientists from traditional business analysts or any statistician out there is that we spend a lot of time writing code. And so some of the options that we have for being able to do that are listed here. They may be familiar to you. Some of you may have heard of some of these languages out there. We'll talk about them a little bit more particular. So some of the other options out there, obviously you've had exposure to some of these like Microsoft, excuse me, Excel. All right. To date, I've never really been able to work on a data science project where everything can be done completely within some kind of graphical package, which is what I consider Excel and Tableau to be. All right, so these are really visualization tools. They're great for some really simple analysis. Like I said, sometimes when you just need to do a quick little summary of a data set or something like that, you don't need to go write a complex program to be able to do that. Sometimes you can visualize that. So Excel and Tableau have very good visualizations. They're really built for being able to do that quick. Tableau is a little bit better for working with different types of relational databases, and so it's limited in its functionality, but its graphics are really nice and integrates good with different database systems. Some of the limitations of these software is that they really do assume that your data is already in a tabular form, meaning that it is in nice rows and columns. All right. So if you have data sets that are more complex and you're looking at, say, things like audio or video or different files, trying to skim websites, all right, these don't do that, right? So really your data sets have to be in nice tabular forms, all right? Data wrangling is also difficult and limited with these, all right? The other software tool you guys may have some experience with is looking at MATLAB. MATLAB is a very popular language that is used with a lot of different computer scientists. Octave is the free version of MATLAB, so you can get Octave. You can use it even on a web-based service now, and you can download Octave and use it for free. The reason why I say that is one of the limits that I think is with MATLAB is that it is expensive compared to other software packages. All right. A lot of people within the traditional sciences, physics, engineering will have background or know something about MATLAB. All right. And the other, some of the other benefits is it has really, really nice GUI interfaces. So you don't have to know a whole lot of complex programming to be able to interact and use MATLAB. The other thing I like about MATLAB is that it really has kind of standardized its algorithm uses. All right. And so there are really only one or two different algorithms really one that has been vetted within the MATLAB family. So if you're going to use a neural network within MATLAB, all right, and say you're going to go out and publish that particular article, all right, you're going to say, hey, I use this neural network within MATLAB. Everybody that has used MATLAB understands what that neural network is and how it's utilized and how it's been vetted, all right? And so that's one good thing is that it's kind of standardized the toolboxes that are used within MATLAB, and everybody that uses MATLAB uses them, all right? Some of the limitations, again, it's expensive, all right? It oftentimes uses this black box design because you're using this GUI interface and things like that. You may not actually know exactly what is happening in the background, all right? And so that's what I mean by a black box design. All right, you just feed it some data. You say, boom, do this. It's going to give you some output. But really, what is going on behind the scenes is what you want to understand as engineers and scientists, not just throwing it in, arbitrarily into this void and getting some information. Some of the plotting functions are limited and difficult to work with. And so oftentimes you will end up taking your output or whatever you've got and manipulate it in another software program, especially when it comes to publications. And so this is a little bit of a limitation. Python is a largely popular language. It's become more and more popular here over the last few years as it deals with IoT stuff, things like Raspberry and Pi, or Raspberry Pi, excuse me, it has become really popular with all of that stuff as well. All right. It's been around since 91. It's really what we call a high-level scripting language. All right, it has a lot of functionality that's similar to R, Perl, if you've heard of that, Ruby as well. All right. Syntax for being able to work with Python is really easy, readable. People can get in this language pretty quickly. One big benefits is that everything is open source, so there's lots of computer libraries. Lots of methods for being able to do different things. All right. A lot of the packages within Python are also developed for the software language R. So both of these languages are pretty interchangeable when it comes to the different packages that you're using. All right. And there's a lot of different frameworks that allow for this programming language to be extremely flexible. Some of the limitations are the compiler's a little slow. And it doesn't have a lot of, some of this is changing. It doesn't have a whole lot of work to do with database, so integration with databases is limited as well. I've also had some trouble being able to get Python to work well with different multi-core, multi-processors stuff, so we've had some issues with that in the past. R is a really cool programming language that I really like, mainly because it was built by statisticians. So R is based upon a programming language that has been around since the 70s called S. All right, and so S was actually a programming language that was built by statisticians. Remember when I said you had this area of statisticians who were working on all these other complex data sets that didn't really fit the traditional mold of a statistician? And so these statisticians came out and said, look, we need our own programming language to be able to analyze this type of data. So they developed S, and that ended up molding into and becoming R. All right. And so some of the benefits of this is that because it was built by statisticians, there's a whole array of different statistical techniques in here. A lot of different modeling, machine learning modeling as well. All right. And then because it's an open source as well, users submit different packages for a variety of different reasons. And so some of the limitations are some of the same limitations that I see in Python. One is because it's open source like that, it's not like MATLAB where you're just going to have one particular model for one. You're not going to have one neural network. You're going to have a whole host of neural networks that are available out there in different packages. And so really, it's up to you guys to decide which one is the one that you want to use, which one's going to be the best one for your application. And that oftentimes requires you guys to understand what is going on behind the scenes with these different algorithms, right? And so if you go, okay, I used this neural network from this particular package, really, why did you use that particular package? All right. Did it fit the data set that you're using? Did it fit a specific application of the data set that you're actually analyzing? And so what's really going on behind the scenes there is important for you guys to understand. All right. And so there's going to be multiple ways for you guys to be able to do the same thing. All right. SAS is another programming language. Just to make you guys familiar with this, it's used a lot in business analytics. All right, it's also used a lot in finance, and so the thing about SAS, I give it some props here. That it's been around for a long time. All right, it's been around since the '60s. It does a great job at different analyzing traditional business statistics. All right. It's got a huge job market. All right. So if you're really looking at doing business analytics or going into fintech out there, it would be good for you to understand or know how to at least work within SAS. I mean, the scripting language isn't that difficult to understand. It integrates very well with a lot of different Microsoft products, and so if this is something that interests you, definitely look into it. The limitations of this is that like MATLAB, you have to pay for it, all right, and it's expensive. It's not open source. Sometimes the language, especially if you've been learning how to program in say Java or Python or R or any of these languages, the language may be a little bit more difficult, alien to you guys than what's being used these days. Plots, diagrams are all pretty simple and general. Like I said, this was really designed as a software tool for people working in finance and business. So if that's an area you're interested in moving into, definitely look into this language a little bit more. All right. So the last little bit here is to introduce you guys to some different open source deep learning frameworks. So these are frameworks that are built and exist within, say, Python and R and other like Java languages. And so these are what I actually consider black box type frameworks, all right, for implementing different machine learning algorithms. And so the reason why I put this slide in here is because when I started researching what this lecture was going to be, I looked at a lot of different job postings, and a lot of the skills and technical skills they wanted involved several of these deep learning frameworks. And so even though in this course you're going to learn what is happening behind the scenes and the backbones of these frameworks, it's important to keep in mind the higher level look of machine learning and how to integrate them into your languages. So scikit-learn, TensorFlow, PyTorch, Torch are all frameworks that can be implemented into different languages like Python and Java and things like that. They oftentimes require a little coding experience, and I mean you're not going to build a new neural network. You're not going to build a whole new algorithm for these. You can put in your information and get some kind of results. And then most are going to have some kind of GUI interface that allows you to integrate your data sets into these frameworks. Like I said, the limitations are these are black box models. All right, difficult to know what your model's doing in the background, but that's why I've designed this course for you guys to be able to look behind the curtain and really see what is going on in the decision process of these different models. And so because of the black box type modeling, it's very easy to do things badly, even though these models are going to give you some kind of output. And so it's very easy for you guys to mess things up quickly. All right. So that's just a little bit of stuff I wanted to touch on today, introducing you guys to the biomedical informatics, data science area, big data, the terms that we're going to be looking at related to machine learning. If you have any questions, and then some of the tools that are important for data scientists to understand. So if you have any questions, feel free to reach out to us. And that's it. Thank you very much. Talk to you later.